Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
For more than 100 years, the sound of transportation was the sound of explosions. Inside petrol and diesel engines, fuel burned thousands of times per minute. Pistons moved up and down, crankshafts rotated, gearboxes shifted, exhaust gases escaped. Heat, vibration, noise, and mechanical complexity became the very identity of automobiles. But today, one of the biggest revolutions in transportation is almost silent. An electric vehicle can move from zero speed with instant torque, without clutch, without fuel injection, without exhaust, and in many cases without a multi-speed gearbox. At the heart of this revolution is not just the battery. The real muscle is the electric motor. Inside modern EVs, three motor technologies dominate the discussion: PMSM, permanent magnet; synchronous motor; BLDC, brushless DC motor; and the induction motor, the legendary AC motor made famous by Nikola Tesla. Today, we will understand how invisible magnetic fields are replacing pistons, crankshafts, and combustion. The story begins in 1820 when scientists discovered a powerful truth. Electric current can create magnetism. When current flows through a wire, a magnetic field forms around it. Wind that wire into a coil, and the field becomes stronger. Place that coil near another magnetic field, and force is created. This simple principle became the foundation of the electric motor. In 1831, Michael Faraday demonstrated electromagnetic rotation, creating continuous motion. Then, Nikola Tesla developed the AC induction motor in 1888, a historic breakthrough designed without brushes or mechanical contact. Factories, pumps, and elevators all began using AC motors, a legacy modern EVs have brought back into the spotlight. Every EV powertrain has three major parts: the battery pack to store DC energy, the inverter to convert it into controlled AC, and the motor to convert that electrical energy into mechanical rotation. In a petrol engine, power is controlled by fuel and air. In an EV, power is controlled by electrons and magnetic fields. Almost every EV motor has two major sections. The stator is the stationary outer part containing copper windings. When current flows, magnetic fields are produced. The rotor is the rotating inner part connected to the output shaft. When magnetic forces act on the rotor, it spins, driving the wheels through the basic magic of electric propulsion. The permanent magnet. Synchronous motor, or PMSM, uses permanent magnets in its rotor, often made from rare earth materials like neodymium. The stator's rotating magnetic field acts like an invisible hand, and the rotor magnets act like a compass needle, locking onto the field and spinning at the exact same speed. This is why it is called synchronous. PMSMs offer high efficiency and torque density, meaning they produce more power for their size and weight. Because the rotor doesn't need current to create magnetism, they have lower losses. However, the magnets rely on sensitive supply chains and can lose strength if exposed to high heat, making advanced thermal management and cooling essential. Next is the BLDC, or brushless DC motor. Older motors used physical brushes that created friction, sparks, and noise. BLDC motors remove the brushes and replace them with smart electronics. The controller energizes different stator coils in sequence, magnetically pulling the rotor magnets forward to create continuous, reliable rotation. The main difference between BLDC and PMSM is in the control waveform. BLDC uses step-by-step electronic switching, while PMSM uses a smoother, sinusoidal wave. This makes PMSM quieter for luxury passenger cars, while BLDC remains a cost-effective and efficient favorite for e-bikes, scooters, drones, and auxiliary vehicle systems. The induction motor is a legend. Unlike the others, it needs no permanent magnets. Its rotor has conductive bars arranged like a squirrel cage. The stator's rotating field cuts through these bars, inducing a voltage and current. This induced current creates its own magnetic field, and the interaction between the stator and rotor fields produces torque. In an induction motor, the rotor must spin slightly slower than the magnetic field, a difference called slip. This slip is essential to induce current and create torque. Induction motors are rugged, durable, and magnet-free, handling high speeds and temperatures better than magnet motors, which is why Tesla famously chose them for his early high-performance vehicles. The inverter is the brain of the system. Using power electronics like silicon carbide MOSFETs, it switches battery voltage thousands of times per second. Modern EVs use advanced methods like field-oriented control to separate current into flux and torque components, allowing the motor to respond to the driver's intent within milliseconds. This precise control is why EVs feel so fast. A petrol engine must build RPM before reaching peak torque, but an electric motor can produce its full turning force from zero speed. There is no clutch delay, no turbo lag, and no engine breathing limitation. Torque isn't waiting for combustion, it's waiting for current. One of the greatest advantages is regenerative braking. When you lift the accelerator, the motor reverses its energy flow, acting as a generator. Mechanical energy becomes electrical energy, sent back to recharge the battery. This improves efficiency, reduces brake wear, and gives EVs their famous one-pedal driving feel. Because EV motors operate efficiently over a wide speed range, they often use a simple single-speed reduction gearbox instead of a complex multi-speed transmission. This reduces mechanical loss and maintenance. In an EV, every watt matters. Motor efficiency directly affects your driving range, turning nearly all battery energy into motion. EV manufacturers carefully match motor type to the vehicle's mission, from city scooters using BLDC to performance SUVs using PMSM and induction combinations. And while they are quiet, they aren't silent. Engineers work tirelessly on NVH, noise, vibration, and harshness, to manage motor whine and gear noise, ensuring a refined and peaceful driving experience. Inside, these are highly engineered machines made of electrical steel laminations, precision bearings, and copper windings. Many modern motors use hairpin windings, rectangular conductors that fit more copper into the slots, reducing resistance and increasing power density. Every material, from the insulation to the steel, is optimized for peak performance. At high speeds, motors face challenges like back EMF, which software manages through field weakening. The future of EV motors is moving toward 800-volt architectures, higher power density, and rare earth-free designs. Engineers are constantly improving cooling and manufacturing to make the transition to electric mobility even more sustainable and powerful. The internal combustion engine is a mechanical masterpiece, but the EV motor is a digital one. With fewer moving parts, instant torque, and digital precision, it is transforming transportation. From the synchronous dancer of the PMSM to the rugged induction legend, these motors are the heart of a software-controlled electric future. Next time you see an EV move silently, remember, there is no explosion, no piston fighting gravity. Instead, there is a controlled storm of electrons, a rotating magnetic field, and a rotor chasing an invisible force. This is the science of the electric machine. Electricity becoming motion.